I'm happy that we have with us Professor Suheshkumar Singh from ISAT Trivandrum, and he's going to talk about photoacoustic imaging and light sheet fluorescence microscopy. And this is towards diversification of imaging technologies for different applications. And so I'll talk a little bit about Professor Suhesh. He did his master's at JNU in the year 2002, and then subsequently did his PhD from Physics Department in Institute of Science and from 2005 to 2011, followed by his postdoc at the University of Florida. And then briefly, he also worked at General Electric, GE. Then subsequently, in 2015, he joined ISAT Trivandrum as an assistant professor, and now he is an associate professor there. His research interests are basically photoacoustic microscopy and tomography, light sheet microscopy, speckle contrast. So a lot of kind of technologies or imaging, technologies that he is using. And I think we are going to see a very enthralling season, his talk. And yeah, I'll just ask Professor Suhesh to take over. Please come, please. Yeah. Thank you.
Yeah, firstly, I would like to convey my hearty thankfuls to the Professor Mandal for the nice introductions, and then of course my senior from the lab. And then again, I'm very thankful to have this opportunity to present our research work, more specifically in the fluorescence light sheet microscopy and then photoacoustic that we are doing over there in ISAT Trivandrum. Okay, so so as I outlined, I will start off with brief introductions about imaging, and then of course it is of very diversified applications, industry, basic science, and clinic, and all the things. So in this talk, I will be focusing on these biological applications, more specifically for the light sheet microscopy, and then photoacoustic microscopy for the clinical applications kind of things. And then I will try to convey the entire experimental setup and the instrumentations. And then of course you have the brief idea with the lab visit, and then the validation study in the tissue mimicking agar phantoms, and then exercise, and then alive sample kind of things. And then I would like to convey with the future direction where we can go ahead it. That is what. So, yeah. So, see, if we look back about the imaging point of view, in our entire life, in the present day, there is no aspect of the present world. It doesn't touch anything about imaging, starting from the photography, videography, games and sports, and then astronomy and astrophysics, and then industry for the detections of the crack in the wall or whatever, and then see about the GPay nowadays, see, pockets, bank in our pocket, right? So everything, all these things is the matters of the imaging and image processing. So not only that one, say clinic, whenever you are going to the clinic, then scanning, right? X-ray, MRI, CT, or whatever, okay? And then say from the basic science, biology, not only from the biology, then physics kind of things, DM, STM, whatever, right? So it is a part and parcel of the one slide now about the imaging and image processing. So yeah, in this way, today I will focus on the biological applications and the clinical applications. So before going in depth about the imaging for the biological applications, that I would like to say that is the biological imaging. So it has a deep history. So since time immemorial, we are quite familiar with the imaging kind of things, not with the present day-to-day technology point of view with our naked eyes. So we have been much using with the single magnified lens, and then simple microscope comes, and then slowly it comes to the confocal microscopy in 1960s, and then in the 1990s it comes to two-photon imaging, and then the super resolutions in 2009. This is what the state of technology as far as the imaging is concerned. Okay, so today I will focus on the LSFM, where we are focusing on. Of course, you are quite familiar. You are shown about the super resolutions also. So similar is the case Similarly is the case for the clinical imaging or imaging technology for the clinical applications. It has a very deep history since the time immemorial. So whenever we are visiting to the physicians, then what we do is touch the hand, gathering the information from the patients, then what is that kind of the input and output kind of things. So what we are doing about is then when we are keeping the presses, we are giving the presses, and then at the same time, our hand is receiving the response from the tissue that inside it. With that one, we are concluding for this. But this kind of the technique, whatever we are adopting, it is very limited. So it is very subjective. It cannot detect a very small, in the sense that disease cannot be detected in the very early stages kind of things. Out of this one, in 1895, it was the Renzel who discovered the X-ray. Then this X-ray, on his way for the study for the physics applications, then he got the images of this one to his wife, and then with this one, people start applications for the clinical studies, okay, for the clinical diagnosis, and then and then ultrasound comes in the 1917s, and then for the clinical application, it was used in the late 1930s. Okay, so then it comes in the 1960s, CT, MRI, PET, and all these things. So, if we look back, if we go to the clinics, then so it becomes as an indispensable, because the kind of the diagnosis technologies without this one is very limited. Okay, so it has been served as a primary clinical tools in the present day. Okay, so however, all of this imaging system has advantages and disadvantages, in a sense that this kind of the X-ray, it is good for the hard tissues, and not hard tissues, I can say bone and all these things. It doesn't work for the soft tissue. And then it is hazardous to health, and then it gives the 2D image, not a 3D image, in the sense that we cannot localize where is the structure is. So then people started with the ultrasound. With this ultrasound, we can get a 3D image. However, the resolution is very poor, in the sense that we cannot detect the abnormality in the body when it is in the very early stages. Then, however, this CT, MRI, and the PET, they are of the high resolution, reasonably good resolutions for the diagnosis and treatment and monitoring of the treatment also. Okay, so unfortunately, this also is pertained with a lot of disadvantages. Firstly, it is very expensive. It is not suitable for the routine monitoring kind of things, and the resolutions is also not so to the mark. So the best resolutions that is available in the market is now around, say, 500 to 600 micrometers. So it is still limited. People are looking forward to how we can get a better resolutions and a better penetration depth and a cheaper price. Lot of factors people start looking for. So interestingly, but in the late 1990s, then photoacoustic imaging come into pictures with the experimental results shows for the potential clinical application. Since then, it has been widely studied and rapidly growing around the globe. Okay, so it is because around the globe, not less than 100 research labs are now focusing for the photoacoustic imaging. Okay, microscopy or tomography kind of things. If we look back, this kind of data so see, presents it's more than the 4,500 literatures are available, and then when we see it, tapping it, so per day is 2.5 paper per day for the photoacoustic imaging is coming, not only from the biomedical applications, then it is now coming for the other industries and agricultures. And then see, if we look back, the photoacoustic journal was introduced in 2014. So it was an impact. Now the impact is 9.65. Okay, this is a kind of the impact of the photoacoustic imaging. These wide studies and rapidly growing, it is because of the potential and promising technical features that is provided by this imaging modality. Firstly, is that it gives the high contrast and resolutions at penetration depth that cannot be achieved by any of the commercially available imaging modality or technology, including the confocal 2 photons, OCT, electron, AFM, whatever. Okay, so the resolution is very good, but the penetration depth is very limited. Whatever you heard about the AFM and all these things. Okay, so this is provided by the photoacoustic imaging. Okay, see, it is worth to bring to you all that this optics-based microscopy is good for the high resolutions. The penetration depth is very low. It's limited to the mm. That is the transport mean free part of the light. Okay. In the meantime, ultrasound imaging modality is good for higher penetration depth, but the resolution is very poor. So resolutions obtainable is limited to the 500 micrometers kind of things. Okay. So then people start thinking of whether we can get some imaging modality that is in between, where the photoacoustic lies. In a sense that this photoacoustic imaging is a dual modality kind of things, integrating both the light and sound together, where the light is using as an interrogating signal, and then acoustic signal is used as a receiving. So taking both the advantages of the optics and the sound. Okay, so in this way, this photoacoustic imaging, it gives the reasonably good resolutions and then penetration depth of the order of the centimeters. So as of now, people are start thinking of that, how we can stress these regions, that penetration depth be further go beyond the tens of the centimeters and the resolution be go down. Okay, this is what directions people are looking forward it. That is where I am also trying to bring to you. Okay, so another technical feature is the high scalability. High scalability, that is that it is feasible for imaging the single cell to the whole structures of the mouse. This is a reported study. Okay, so in the meantime, say a lot of the structures of the blood vessels can be imaged. It is of the high impact for the clinical applications that I would like to say. Another features that we can say is that it can give the vital pathophysiological informations of the concentrations of the HB, HBO, total oxygenations, and a total hemoglobin that are the characteristics for controlling of the metabolism, molecular, and genetic activities. So by the recovery of these molecular information, one can diagnose and follow up the treatments of any kind of the disease. Okay. So of course, it has a lot of implications for the neurovascular scopular. It is already reported for the neuro applications. Okay. And then lastly, yeah, and then it facilitated to develop the multimodality. So as far as the imaging is concerned, for the clinical applications, the new directions that is what we are expecting is the combinations of all this imaging modality. The idea is that, see, if we go to the clinics, then okay, you take the ultrasound and then you take the CT, MRI, then patients are going next by next. Instead of this one, you just go, then in one room, then everything would be there in imaging system ultra. This is what combining all the imaging as much as together. Okay, in this way, photoacoustic imaging is a good candidate to develop a multimodality. Okay, so and then lastly, it is non-hazardous and then safety to health because it doesn't use any of the ionizing radiations, and then it doesn't need to cut the sample into the pieces, and then it doesn't require to introduce any kind of the drug or these things. Okay, if required, we can do it, but it is not mandated. Okay, these are the features. So Liu Hong Wang, in one of these pieces, I used to call it, it is long back, 10 years back, he says that photoacoustic imaging is seen as an alternative, future alternative to the X-ray and then CT and MRI kind of things. Yeah, from my side, I would like to say at least combination of the photoacoustic and these regions. Okay. Okay, so till now it is reported for the various applications, biology, oncology, and all those things. Okay, so the other directions now presents people are looking forward is for the brain imaging. It is the new directions for the photoacoustic applications. And then in the meantime, people are looking forward in what way that still we can exploit the applications of the photoacoustic imaging. And another one is that, how we can improve the resolution, penetration there. These are the few also directions people are looking forward in. Okay. So from the prospect point of view, so I'm just showing a few. So till now, 10 to 12 company are here around the globe. And then these are the few that gives in the markets the photoacoustic imaging system. Just to clarify, this is the imaging system for the laboratory use, not for the clinical use. Why? It is not from technology. This is from the ethical approval. The good news is that in the last 1 year or 2 years, it is already approved for the breast cancer diagnosis for the photoacoustic. That is the good news. So from this one, we believe that in the near future, in these 2 or 3 years, then it will be rolled out for the clinical applications. So this photoacoustic imaging is fundamentally based on the photoacoustic effect. That is the phenomenon of generations of the sound wave by illuminating the sample with a light beam for the short durations. So basically, this photoacoustic effect was propounded in 1880s by the Alexander Graham Bell. Okay, it was used for the basic science studies, mostly for chemistry, and then it was not exploited for clinical applications. It was only in the late 1990s only it was started for the clinical applications. What is happening is that when the pulse light is illuminating on the sample, then this sample will absorb the light, then it will induce the increasing of the temperatures, then it will induce the expansion. But this illumination is very transient. It is of the order of the nanosecond. This expansion is very, very transient. Then it will contract back. And because of this one, it induced the thermoelastic expansion. That is that optical energy is now converted to the sound energy. Okay. So this is what we call as the thermoelastic expansion. This thermoelastic expansion is given by this equation. This is the intensity of the or pressure of the acoustic wave against the optical fluence. Okay. So as a parameters, it is the optical absorption coefficients and then thermoelastic expansion, thermodynamic parameters, that is the thermal coefficient of the expansion and then acoustic velocity and the specific heat capacity at the concentrations. So at the very beginning of the photoacoustic imaging, from the experimental measurement, some way or other of the P naught, whether we can get it, these mu distributions of the optical absorptions with the given that optical fluence. So what people now started is that not only from the mu A, whether we can recover all of these physical parameters out of this. Next, with this physical parameter, is there any implication for the clinical evidence? This is one. Okay, so mechanical property we can recover it, that has a huge application for the clinical studies. Okay, and then for the diagnosis. Okay, so as we are conveyed by the clinicians that lot of the disease that remains silent out of this recovery of this elastic property. In other words, that if we can recover the elastic property distributions in the body non-invasively and non-destructively, we can unlock a lot of the diagnosis for the diseases. This is what. Okay. So now I will move about the development of the imaging. So this photoacoustic imaging is broadly divided into the two groups, that is the tomography and microscopy. And the microscopy, again, it is divided into the optical resolutions and the acoustic resolutions. In this tomography, what is that? Light is illuminated then an array of the acoustic sensors are kept on the boundary of the sample, okay? Or otherwise, one array is keeping, then it is moving around. So what? They are collecting the acoustic signal from the boundary, okay? From this boundary measurement, then we recover the initial pressure distributions here by solving the differential equations iteratively, or otherwise by using some kind of the other technique. That is what I'm going to come out, delay in some kind of the technique without solving this kind of these things. This is also a diversified area for the reconstruction of the images, okay? So, and then in the photoacoustic microscopy, what is that? Is these expanded beams are doing, and then tightly focusing ultrasound transducers are keeping around here. Over here, it is not focusing transducer. We may use it, but not necessarily. So then, if we are focusing with these transducers, then we are collecting a time-resolved signal that is enabled by the data acquisitions system, okay, along a line that is the 1D time-resolved signal that we can collect it, okay? So in this way, then the obtainable spatial resolution is controlled or detected by the spot size of this focusing transducer, okay? However, in the case of the OR palm, then what? Instead of the extended optical beam, they are using a tightly focusing optical beam, which spot size is much smaller than the focal spot size of the shunt, okay? In this way, then the resolution is controlled by this optical beam. The advantages is that it gives a better spatial resolutions, but the penetration depth is very limited. The penetration depth is limited to the 1 mm. But for this one, penetration depth can go up to the millimeters, 5 millimeters. Safely we can go up to the 5 millimeters. Okay, this is the trade-off. This is where I would be focusing on, not the OR one. Okay, so only the difference is about the configurations in the detections, okay, or illumination to an extent. Okay, so it is worth to say that in this microscopy, either it may be OR palm and an air palm and all this thing, it has a trade-off. The idea is that the kind of the resolutions that can be obtained by this OR palm, whether it can be achieved by the air palm, or otherwise, at the same time, penetration depth is still maintained, or otherwise, OR palm that extend the penetration depth, resolution is maintained, stretching the region. Okay, so this is what people start looking for it. So this is where I would be talking about how we can do it. I am presenting some kind of the technique that can be able to that enable us to extend the microscopic resolutions to the order of the centimeters. Okay, this is the experimental systems where this light from the pulse laser source is coupled to an optical fiber and then illuminating over here, and then acquire the photoacoustic signal by these transistors, and then it is amplified and then collected by the computers. Okay, at one scanning point we get the 1D data. So what if we are scanning this one along one direction, then it will give the 2D data, and then if we scan to the 2D, then it will give the 3D data. So what? By scanning the sample with this holding unit that is connected to the stepper motor, then we can get the image of the samples. Okay, this is the raster scanning based imaging technology that we can say. So yeah, of course it needs the high automations of these systems. Okay, because the pulse laser is of the 6 nanosecond, and the lifetime of the photoacoustic signal is of the order of the microsecond. So once firing, then we have to acquire it. Then we have to move it. So firing and the acquisition has to be perfectly synchronized. So we need a synchronization of the systems. So this time-resolved signal, this time-resolved signal is converted to the space-resolved signal. So instead of with respect to time, then we can get it with respect to depth. Okay, so depth resolved signal that we can get it. So one disadvantages for the presently available photoacoustic imaging system is that, see, this is a telefocusing ultrasound transitions. Then what? This time result signal is the measurement at a particular time. This particular time measurement is average over the sectoral areas, that is the intersections of the focusing beam and the spherical wave generated from this point source. So what? The resolution, obtainable resolution for this photoacoustic microscopy is controlled by this beam. Okay, so as it is away from the focal spot size, then it is gone away. Okay, so then what? We assume that over this focal length, then what? This area is assumed to be uniform. Okay, then this obtainable length through which this is uniform, theoretically we can calculate it, that is of the 150 micrometers only. It's very limited. The field of view along the axis is very limited. And then, so if we are doing, see, this is the theory all about it. See, this is the reconstruction by using this one. So what? We cannot do the imaging of the target down this one, not beyond this one. Only this one is reconstructed well, others are not reconstructed. So we are not able to get it. So the application is very limited for the biological application. Then what it says, the sample size should be limited to that of this 150 micrometers. So it is very limited. So then what we do is that whether we can stretch this focal zone length to the order of the centimeters. That is what we are talking about while maintaining the resolutions of this 25 micrometers kind. Okay. So yeah, this is what I was talking about. It is very limited because of the obtainable resolutions and then field of view or this one. Of course, this is the characterization studies for the obtainable focal zone length along the axis. Okay, experimentally, this is the experimental data, is not a simulated data. Fine. So with our systems, we are able to get this one with the conventional microscopy imaging modality, say this one, XL is the 34, 36, that's all. Fine. So, so in this way, that is what we are aiming to increase the depth of field or field of view from the micrometer to the centimeters. Then what to do? So instead of the directly mapping from the time result signal to the space result, then in the reconstruction, then we apply this kind of the data, that is number of the 1D data, then you sum it up. This one, this is what we sum it. This is what we call as the delay and sum. That doesn't involve any kind of the solving the second order differential equation. So by summing this one, then we can improve the obtainable resolution. See, this is the convention. With this one, with this technique, then we are improving. Okay, this is what we call as the SEF. Of course, this is the technique conventionally used in the ultrasound imaging. Then people start incorporating in the photoacoustic. Okay, this is what the existing one. So our aim of our group was that how far we can improve this kind of the images with this one. So let's see. So in this conventional technique, when we are summing up all these things, they didn't take into account energy loss when the acoustic signal is going with a distance. Okay, so then whether we can incorporate this kind of the energy loss when it's traveling through a medium. So this is what we are proposing with a theory and an experimental technique. Okay, and another thing was that when they are summing up, then they are summing up as a scalar quantity, but this is a acoustic wave. This is a wave. So then there is no coupling term over here. They didn't consider, they sum up as just an intensity, doesn't sum up as a wave. So interference effect was not taken into here. So then why we should not take into here that energy loss and the interference phenomenon that has to be taken here. With this one, whether we can improve it. Just to clarify once more, it is underway that what about if we combine these two? Energy loss is also there. Interference current should be there. It is underway. That I am not presenting today. So with this one, say by taking into energy compensated shaft, then this is the improvement. This is the convention. Okay, this is the shaft, and then background noise can be improved by the coherence factors. then it is not satisfactory, then we do it. See, this is our results. Okay, so this microscopy resolutions from here to here, then we are coming to here. It is from the micrometer regions to the coming to the centimeters. This is our contribution that I would like to say. This is the images for the here human hair embedded in the agar samples. Okay, this is the control sample, I would like to say. Then we try it whether this kind of the technology is quite applicable for clinical translations. Before moving that one, what we're using is that lip band. So 3 leaf, then we remove the softer part by some process, then it remains only the some kind of the that mimics as the blood vessels. So we are quite successful to reconstruct it. This is the conventional self and all this. So the contrast resolution is quite improved. Okay, so then we test that for the chicken breast, and then over there we embedded with the pencil lead that is mimicking as a blood vessel, and then at the same time we do it for the this one in the agar also. Okay, so this is what I was talking about as an ex vivo samples, whether for the transitions to the clinical applications. Next, other applications what we are looking forward is that if that is the case, whether we can use for the ophthalmic applications. So as of now, whenever you are going to the this one ophthalmology, then what you are doing the imaging. If we seriously look back, what they are doing the imaging for the retinal part. That is what. But if we need for the other cornea and other stuff, then they have to switch from the imaging technology point of view. What I mean to say is that with the existing technology, it's not possible to see the whole eyes at one time. We have to do it one by one. We cannot do it. So this kind of the technology, whether we can use for the whole eyes imaging kind of things. Okay, so this is what we are trying. This is the excised tissue. Of course, it is not alive. Alive, it is underway that we are going to do. So then this is the reconstructed image. So this is the reconstructed image. This is projected in the 3 mutually perpendicular plane. Okay, so then we can recover all the structures in the retina, top part, side, lens, and all these things. Okay, that is what we tried. So this is what, as you say, that we projected to the other plane in a different regions kind of things. So yeah, this is about the analysis for this one. So we can see from this one, we can clearly see the vascularizations in the retina and in the other part of the posterior and the anterior part of the eyes that we can do. Okay, so yeah, see over here we can nicely see the things. Okay, this is another one applications. So another ones that I was talking about, the correction from the interference point of view. So if we look back, it is well reconstructed over here. So it is, I missed to mark it. So it is of the order of the 1 centimeter from 1 to 12. So penetration depth is of the order of the centimeter, maintaining the lateral resolutions to the 30 to 40 micrometers. Okay, so this is our contribution. Then we tried the validations in the same way that we did it for the ESF. Fine, sure. In this way, depth of field was improved by 25%, and then axial resolution improved by 20%, and the lateral resolution in this way. Okay, SNR also quite improved. Okay, this is what we did it for the photoacoustic microscopy, and we also do it for the tomography. So for in the array, we are not moving scanning one by one. Then we give the array of the transitions. Then we do the reconstruction algorithms. We do a good number of the reconstruction. More specifically, we are focusing for the real-time reconstruction kind of things. So this one, we tried it for the volunteers and over here, the potential for recovery of the blood vessel in the right side that we can see. Okay, yeah. So, and then so many phantom also we tried. So this is about tomography, and then we tried it for chemistry applications kind of things. So some fabrications of the nanoparticles, whether they have the photoacoustic effect kind of thing, that is aimed for the clinical applications. So this is our yeah. And at the same time, we also try it for adaptations of these micro machines technology of the PMUD ultrasound sensing systems, and then do it that one potential applications kind of things. So this is for the single cell PMUD system. The size is very small. I didn't show the but no, I missed it. Okay. So it's very small, then it will be able to miniaturize the imaging system very small. Then what it helps, the ultrasound, that one keeping over here, it fails to reach the proximity of the body. And then in the ICU setting kind of things, whether we can do with this kind of thing, that is what we are looking forward it. And in the meantime, as I have mentioned you, not only that one, whether we can recover the elastic property of the tissues, that is what we are looking forward it. Okay, this is the 2D images for the reconstruction of the elastic property of this one. This is the qualitative image. We are now working for the quantitative measurement. So just to say, photoacoustic elastography is very limited. Say less than 12 literatures are available. It remains as a open problem. Okay. So with this one, I would like to conclude about the photoacoustic. And then now I will move on to the light microscopy. This is our experimental system that may be a little bit different from the one. There a lot of overlap is there. And then say we are beam expanding, illuminating over here. What we contribute in the light domain is that with this kind of systems, instead of this just one single arm, then we put it the two arm. So if these two arms, if we are fitted with the different magnifications in this objective, then we can get it multiple magnifications of the same imaging frame, okay, of the samples. So the idea is that it can get multiple two field of view with the different magnifications or resolutions. Okay, the idea is that when the field of view is large, the resolution is spread out. When the resolution is very high, then field of view is very limited. So when we are trying to see an object with a microscopic resolution, then we lose the field of view of the order of the millimeters. Then what? Side by side, whether we can see the field of view and this one, whether it has a biological implication, yes. So when we are studying about the microscopically over the certain cell and all these things, what is the connections with the surrounding to the whole body, response from whole body, that we got lost. Conventionally, what we are doing is that we are adapting one by one, but it lost the time resolution. We cannot get it, and then very conversion. This one with this one, we are able to see simultaneously. Okay, so this is whole structures about architectures, about the controlling system and all these things. Okay. Yeah, this is the validation study that we did for the simultaneous magnifications kind of this. This is the zebra fish. See, over this one, this is the 10x or so, then field of view is very large, but it lost the resolution. So it gives a high resolution, but it lost the full view. Then if there is any study for the drug control and whatever, then we can see both this side. If what is happening over here, in the meantime, what is happening over here, we can see simultaneously. That is the idea. And we tried it for the neuroimaging also. So this is about the neuroimaging in the Drosophila. And then not only with this one, then we can do the reconstruction, the 3D images with the multiple magnifications. Okay, so this is the reconstruction of the whole 3D of the zebrafish. Okay, so yeah, so this is what we were contributing and all these things. With this imaging system, one other difference is that we are using the tunable pulse laser rather than CW lasers. The idea is that, so the kind of the pulse laser we are having is say 400 nanometer to 750 nanometers. Then at any wavelength, then we can excite it. Okay, so that is the idea. So then we do the validation study for the time dynamics of the biological phenomena. Okay, the development of the textile systems in the Drosophila. So this kind of detection system is very similar with the blood vessel development in the human body. Okay, the biologically they studied in the traction development kind of things. So this is the 3D image obtained with the 11x simultaneously with the 24x. We can do it with the 40x also. So we didn't include that image over here. Then we are tracking all these things. Okay, with the image processing. Okay. And then the sample we are using is of the stage of the development of the 17 stage. Okay, this is for the fixed sample. It is fixed in the agar. Okay, it is not alive. So then this is for the alive images. We are tracking and then plotting the length of the track. So for some kind of the branches, it doesn't start up to the T0 30 minutes. Then it will start growing. However, it is saturated. This is what. Okay. There is no video, right? Yeah. Let's see whether this is a. Oh. Then I have to play one by one. Okay. It is supposed to. Yeah. This kind of the time dynamics we are recording. Okay. How is developing? And then image processing point of view, how the tractions are developed over here. Yeah, similarly for the earlier stage of the developments, then we can get it for the 10 to 12 also we can see. We try it for where there is not much development of the tracks here. Okay. So I mean to say the structural development mostly start from the stage 12 and above kind of things. Okay, this is with the okay. Oh, it is still working. Fine. So let's see. Oh, video is not playing. Okay. So yeah. Other stuff that we are doing about is the dynamics of the mitochondria. Okay. So this is shown for the 11x. This is for the 44x. We can sense the benefit accordingly what we want, and then see. Then we recorded a video how these mitochondria are moving. Okay. See, this is how the mitochondria is randomly moving all around. So the random moving, it is under process that it is not. Yeah, and then we also study about the sucking of the waters by the plant. We tried it for the onion roots, keep it in the waters, and then how water are sucking up. Yeah, just a simple experiment we did it before moving for the other structural development and all those things. Is it over? No. Yeah, and this is the last, I think. So for the multiple wavelength, we check it to the systems to image for the nucleus and tubulins. Then we are imaging, then it is fused together. It is not so clear over here. Over here is clear. Okay. So what? So with this one, multiple photon tagging, if we have it, then we can do it. Yeah, just to convey it with you, we are facing the challenges from the biological sample preparation point of view to take it for the 3 and more. Yeah, quite successful to take for the 2. And if we are given with that one validation study for the multiple wavelength that we can do. So with the system. Okay. Yeah, in this for the pressure direction, as I have conveyed to you in so many ways, that we can try to recover a lot of the information what the doctors need for the clinical applications, and then what the biologist needs, what is the technology we can look for what it. Okay, so then we have a long way to go. Animal model clinical trials and then all this commercialization and clinical uses. I think with this one, I would like to convey my very acknowledgements to my first students. That one, they developed the photoacoustic, he developed the light sheet, and then there are the presents, and then they are conducting for the this one, all ice measuring done by this one. Okay, so yeah, not less, I'm very thankful to the Professor Partha, with whom I have been quite long associating with it. I'm very thankful for introducing me about the beauty of the light sheet microscopy, and then support from the Upendra and then Professor Murthy, deputy directors of our institute, and then Jesse Burgess, and who give me the samples. And very interestingly, input from the clinician is very exciting. Sometimes they feel that, oh, it's very tough. Then, oh, technology is simple, we can do it. Sometimes they say it's very easy, technology is very challenging. So sitting together is very helpful. So from my side, I would like to say now it's time that we have to sit all together. Biologists, physicists, technical, whatever better. And then not that one. Now is the time that, oh, I am the mathematician, I don't know anything about biology. It's not the time. We have to gather all the information as much as possible. That I would like to say. With this one, I would like to open for the questions.
What is the actually resolution that you have somewhere in nano or in micro?
Photoacoustic, see, the microscopy resolutions for ORPA, they are giving the resolutions of the 500 nanometers.
500 nanometers.
500 to 600 nanometers. They have a single cell imaging, they have done it, but the penetration depth is the surface imaging. And then air pump, it is giving the resolution say 15 to 20 micrometer. We got it around 30 micrometer, but the penetration depth is for the centimeter, millimeter, 4 to 5 millimeter sadly. And then tomography, the best possible is the whole mouth, that is the 200 micrometer. And the penetration depth of the order of a few centimeters. That is
This photo it is coming from like absorbing the photo.
So then you will use the heating, temperature rise, and then expanding, but it cuts off. Then it will contract. And then it has a tendency to expand it again. It doesn't stop everything. So what this is illuminated area, then what is expanding, contracting. Then it has a tendency to go here. Then I am doing the contracting in this one. Then I am connected with you. Then you will start here, right?
It is nothing to do with the process.
Nothing.
It is like
Completely non-interest. If we want, we can do it, but it's not like that. And then light is completely within the circuit.
Okay, I think we should thank the speaker, and really a good talk, very interesting talk, and multimodality is something embedded in it. It's really nice. So yeah, I think we have already done the question answer. So if anyone else want to add up,
Yeah. Yes, so now we are using the condensed ultrasound foundation. We are using the array. We are using the array. For the microscopy, we are doing a single element, then it is started scanning all around. And then one scan it will be the 1 liter, 2 liter kind of thing. But for the tomography, we can go around 1 by 1 single element. That also one. But it compromise with the temporary resolution. Then if we are doing a array of the transmitters that are occurring simultaneously, that is what we are. So I missed to inform about that one. The one for the tomography we are doing, we were doing was the 16 element. Conventionally, as of now, SSL is the 128 element. So what the price of the instrument is going to be drastically different. But we are very confident that our results are quite comparable to them. So that is the one. So that is what the process used to say. So it is sometimes good if we don't have the money, then we have to put our hands.
some vacuum kind of thing.
No.
So this sound,
No. Yes, why? Because this is our the frequency in our environment is of the order of hertz. This is the megahertz. Photoacoustic is a broadband. So kilohertz to the gigahertz. People has already reported.
you have shown the data for the Gila cell in that
Yes,
decided or detection.
yes.
So how do you place that sample?
Basically, we place vertical. So,
Vertical, like this with the image.
yeah, let's see, it has to be completely 90 degree. So, if that is the case, it is looking the light illumination over here. It's looking that 1 degree or 2 degree. So, we were very worried to play around it, but after trying some time, then.
So the cells, you are seeing the cells like this and you are detecting.
Yes, see, it's still, it is the bit of moving in the yeah,
What is the resolution?
the pixel size that we are having is, we have some camera, ranging from the 3 micrometer to 15 micrometer. So the resolution is detected by that one, not by the diffraction limit. Diffraction is delta by 2, right? So our pixel size is far bigger than this one. So we are not able to get it to the diffraction limit.
Okay, I think we are over time now. So let us thank once more and I think we will talk. We'll go ahead for live. Okay, good.